All right. We have a lot of stuff to get through today, so you can get to the next set of problems. But I could answer maybe like one homework question if anyone has any. Yeah.
Can you show us how to do number 2?
Yeah, of that new set. Do you have it with you?
I do not have it.
Anybody have it?
I think part of it is I just don't understand what you're asking.
That's always
like just the corner. Can't win them all, I guess. Well, there goes for
Okay.
your answers.
So of that set of problems that I gave you on Tuesday, number 2 says, well, what it looks like is you have a beam connected to a pin joint up there. And here there's a pin that slides in this slot. That's something that we're going to see over and over again. And, okay, we have a length of 4 meters. The angle of the beam is 45 degrees with the horizontal or the vertical. And the slot makes a 20-degree angle with the vertical. So if you draw a vertical line, this angle is 20 degrees. What's a vector with a magnitude of r that's perpendicular to that slot? It seems like sort of a random question, but we're going to see soon that that's the force that slot excuse me, the force that slot applies to this member is going to be perpendicular. So the question really is, if you have, okay, so part A. What's a vector with a magnitude of r that's perpendicular to the slot? So here's our coordinate system. There's the positive x, positive y. Our slot is like this. I'm going to draw that as a vector this way, and we know that this angle is 20 degrees. And then what we want is, if we want a vector that has a magnitude of r, that means that we want to take this value r and multiply it by a unit vector. So we need to come up with a unit vector of something that's perpendicular to that blue vector. Okay? There are 2 possibilities. This is perpendicular. And this is perpendicular. Right? So either one of those is fine. We just want one of those 2 vectors. Well, in this case, you can actually kind of eyeball it. I mean, you can see the way that I drew it, that if this angle is 20 degrees, this angle is 20 degrees. So if this is 20, this is 20, and this is 20. But if you don't see that, then go start here at the positive x-axis. There's plus 90, plus another 20. So now, pointing this way, we're at 110. And now either add or subtract 90 to that to get, add 90 to get to the purple vector or subtract 90 to get to the green vector. So 110 minus 90 puts you back at 20. Or if you went the other way, 110 plus 90 puts you at 200. So I'll color code it. So the purple vector, unit vector, is cosine of 200 and sine of 200. The dark green vector is cosine of 20, sine of 20. Numerically, this gives you negative 0.940, negative 0.342. And numerically, this gives you positive, it's just the opposite direction, so positive 0.940, positive 0.342. And now to get a vector, these are vectors that are perpendicular to the slot that have a magnitude of 1. So to get vectors perpendicular to the slot that have a magnitude of r, just multiply either one of these times r. So the answer is, there are two options. One is negative 0.940 r, negative 0.342 r, and the second one is positive 0.940 r, positive 0.342 r. And what you're doing there, we haven't gotten into this yet. It won't be too long till we do, but that's a way to represent the force that that slot applies to the member. And then you have that force vector represented using a single variable r, and you can solve for that r, figure out what the force vector is. What's the vector from the wall pin to the slot pin? So that's part B. All right, it is to the slot pin, the pin that's in that slot, from the wall pin. So the vector that we're looking for is this one, except straight. And so you have to figure out the components of that vector. The easiest way to do that is to put the origin of the coordinate system at the starting point. If this angle is 45 degrees, this angle is 45 degrees. And so it's plus 45 to get there from the positive x-axis, and then you're going 180 to get there. So the vector is the total length, the magnitude of that vector, times the cosine of 45 plus 180 is 225. So I think that is negative 2.82. 2, 8, something like that. Any questions about that one?
But why is there is 4 times?
Because the length, I think, is 4.
Oh,
So you know that the length of this vector is 4, and then you just have to multiply it by the unit vector. Yep.
why wouldn't the force in that slot pin have the specific direction?
On the slot pin?
Yes.
It-
As in we just
it does.
say we can pick either direction. Does that direction
Oh,
matter?
with some joints it does, and with some it doesn't. Well, it does matter, but the thing is, with this kind of joint, it can apply a force in this direction or this direction. So you just pick one, assume it's that, and if you picked wrong, you just get a negative answer. It tells you the same thing.
Okay.
Yep. But you're right that the direction matters. It's just you can choose either one to start with, and it'll work itself out.
Okay.
Whose was this? Yours? All right. So last time we were getting into free body diagrams, and I said that in the free body diagram, well, also in the equations, we're going to make a distinction between loads where we know the direction and loads where we don't know the direction. If we don't know the direction, we just draw like axes in the coordinate directions, unit vectors in the coordinate directions, and associate it with a vector variable. But if we do know the direction, we draw an arrow in that direction and associate it with a scalar. Since we're making that distinction between knowing the direction and not, we have to figure out when we know the direction. Okay, so here are the times that we know the direction of a force. That's what we're getting into here. Okay, so when do we know the direction of a force? And to answer that question, we have to think about joints for the first time. So this will be one of the biggest topics in this class, maybe the biggest single topic in this class. We're just going to do it really briefly here. A joint is a connection between bodies. So, for example, a member connected to a pin like this, that's a joint where the member connects with the pin. That pin connects it to the ground. If you have an object that's like welded to another object, that's a joint, a different type of joint. The one that we just saw briefly was a pin and slot joint, so that's a type of joint. And for this discussion, since we're just talking about what we're starting with here is particle statics, we're just going to be concerned with 3 of them. 3 joint types. The first one is cables. And all cables do is pull on an object. The second one is frictionless contact between bodies. If you have frictionless contact between bodies, then all those bodies are doing is pushing on each other. There's no force applied parallel to the surface. So I'm going to call that a pushing contact. And then the last one is friction contact between bodies. And I'm going to tell you how to represent these when they come up in problems. The first one is cables. And you can also use this approach for any time you know that there's just a pure pulling happening. So a cable applies a force to a body that is parallel to the cable. And acts away from the body toward the cable. The magnitude of the force is constant all the way along the cable if we can make some assumptions. And those assumptions are for a massless cable, that only crosses over massless and frictionless pulleys. Okay, so as an example, let's say we have a cable, a pulley connected to the ceiling, and that pulley connects a 2 kilogram mass on one side and a 1 kilogram mass on the other side. This wouldn't be static, but you could do the dynamics of a problem like this. Then the free body diagram of the 1 kilogram mass is 1 times G acting down and a cable tension T acting up. And a free body diagram of the second mass has the weight of 2 times the acceleration of gravity with T acting up. And the reason that so the directions come from the rules about pulling contact, about cables. And the fact that these are both equal to T comes from the fact that we're assuming this is a massless cable, and even though it touches something else, the thing it touches is a massless, frictionless pulley. Okay, and you can always assume cables are massless and pulleys are massless and frictionless unless a problem says otherwise. Any questions about that? So that's how to treat cables in free body diagrams. That gives you the known direction and the way to treat the variables for pulling forces by pulleys.
For the force of gravity, is the units for the mass supposed to be kilograms?
Yes.
Okay.
I pretty much always do things in SI units. If I see something in English units, I pretty much just always convert to SI units because I'm used to.
Is it supposed to be kilograms and not something like grams? But yeah.
Kilograms is the SI units.
Okay.
Yep. So the next type of joint is frictionless contact. That's a pushing contact. So if two objects push against each other without friction, then the contact force on one body first is perpendicular to the surface of contact. And second, it's toward the chosen body, away from the contacting body. And then the contact force on the other body has equal magnitude and opposite direction. All right, so say that you have two carts on wheels. We'll assume the wheels are frictionless and they're sitting on this incline. So you have one cart here that has a mass of 5 kilograms and one cart here that has a mass of 3 kilograms. And say that you have 100 Newton force applied. Then a free body diagram of the 3 kilogram cart. Looks like this. So there's the outline. The first thing we know is going on is weight. So there's 3 times 9.81. I'll write it as 29.43. The 100 Newton force is acting on the 3 kilogram. It's acting on the boundary. Now we get to the wheels, and there's a pushing contact applied to the wheels by the ground. I'm going to lump it all into one wheel, but you could separate it into 2. But it's a pushing contact, so it's perpendicular to the surface of contact. Being perpendicular to the surface of contact means it's parallel to this. It's either up or down. And then it's toward the chosen body, away from the contacting body, which means this. And you can give it any variable name you want. I'm going to call it N3 for normal. And now keep going around the boundary looking for contact. And there's contact over here. That's a pushing contact. It's perpendicular to the surface of contact, toward the chosen body, away from the contacting body. And I'll call that R. And then a free body diagram of the 5 kilogram. We have a downward force produced by the weight. That's 5 times 9.81, 49.05. What about that 100 Newton force? Is that acting here? No, we're going around the boundary looking for contact, and that 100 isn't applied at the boundary of the 5, so it just doesn't appear. Okay? It's not in here. Yep.
Would still be a force from part 3 from that force we got out there?
That's right. Yep. And so since this is a contact force between those two, that's a pushing contact. So it's perpendicular to the surface of contact, toward the chosen body. And since this is the contact force that produced this R on the first body, we know the magnitude is R here too. And then keep going around the boundary. You get to the pushing contact from the ground. It's perpendicular to the ground, toward the chosen body. I'll call that N5. And then you're done. Yep. That is 5 kilograms times 9.81. That's the weight. Yep.
So our R in the free body diagram 5, would proper notation for that, like with a force vector, would that be like F of 5, 3?
Yeah, if you were going to call that, and we'll talk about that today.
Okay.
If you were going to label that force vector, it would be F5.3, the force on 5 by 3, and this would be F3.5.
So you could also name that?
Yep.
Okay.
Yeah, we'll talk about that. But in the free body diagram, this is how it should show up. Any other questions about that? Yep.
Is it important to have the vectors that are the gravity vector come from the middle of the object?
It's not important yet because we're treating these as particles, so you can just put these wherever you want. But yes, it's important mathematically that we treat it like it's acting in the middle once we start talking about these as rigid bodies that have dimensions. For now, basically, the way to think about it with particles is everything is happening at the center of mass. Any other questions? Yep.
So if you draw the vector same direction, but instead of drawing R in the right, draw it from the left.
That's fine for particles, but again, that's going to, because with particles you don't care You don't care where anything looks like it acts because it all acts at one location. That kind of stuff is going to be more important when we start treating things as rigid bodies later. But for now, you can put it anywhere, just wherever it makes your picture look less cluttered. Okay, and then the last one is frictionless contact. No, friction contact. In Physics 1, with friction contact, you always broke it up into a normal force and then figured out a friction force that was equal to the coefficient times the normal. You don't have to bother with that here. The reason you don't is because this is almost always going to be a static friction, and it's never going to be reaching the, static friction is only equal to mu times the normal force when it's right at the point where it switches over to still to moving. This isn't going to be at that point. And so we're just going to always treat friction contact as an unknown force vector. We don't know either component. Okay, so let's say we have two blocks sitting on top of each other on an incline. A 2 kilogram on the bottom, a 1 kilogram on the top. And we have a horizontal force of 5 newtons here, and a force parallel to the ground of 10 newtons, like that. Then a free body diagram of the 1 kilogram block looks like this. We have the weight of 1 times 9.81, so 9.81 newtons. We have the horizontal force of 5. And then the contact with block 2 is friction, so for now I'll just call that R. If I did a free body diagram of both of them together, we'd have the 5 Newton force like that. We'd have the 10 Newton force like that. We have the weight. Should have done that first. At 29.43. And we're just going around the boundary of what we've chosen to isolate, looking for contact, and the only place we see that along the boundary is the contact between the 2 kilogram block and the incline. So, I don't know, I'll call that F. Any questions about that? Yep.
Yes, I'd just like to make sure that the 5 newtons was acting at a slope, correct?
It was supposed to be like the incline is at a slope and the 5 is supposed to be horizontal, but
okay. All right, just make sure.
yep. Okay. So now I want to give a naming convention. Oh, let me say before I go into this, all this stuff that I'm doing today, this is so quizzy. This is so chock full of quiz questions, you know? It's like a month of quizzes. So pay attention to all this stuff I'm saying. In general, like when I'm up here saying stuff, pay attention to that. That's my intention. Okay.
I have a question for free body diagram. First one, so 2 kilograms is acting on it. Why we didn't draw a force going up?
Well, there's friction contact between these things. And so, like in physics 1, you would have said that there's a force in this direction, the normal force, and then a friction this direction, a force in this direction, that's the friction force. That's still true, but we've just lumped it into these two unknown components. So we're just saying we don't know what those components are. We do know what the normal force component is, but we don't have any way to know without using Newton's laws what the friction component is. So we're just going to say they're both unknown and we'll calculate them.
So there's one going, like for the free body diagram one, there's the 2 kilogram acting up on it.
Yeah, that's all. This R contains all of the forces that the 2 kilogram block is applying to the 1 kilogram.
Oh, okay.
There's just no benefit to trying to break it up into a normal and a friction for us. Okay, so now, naming convention. This is a naming convention that this is going to be used all the time. And we'll see as we go on that it's actually really useful, and that's why these rules are important. Naming convention for force vectors, and this also holds for couple vectors too, which we haven't talked about yet. The first thing, the most important thing to keep in mind about this is it can get you into trouble if you use this naming convention for scalar variables. Even if those scalar variables are representing forces, only use these for vectors. So only use this for force and couple vectors. Not scalars. And the naming convention is, I'll call this the subscript notation or the double subscript notation. The force vector the force vector AB means the force on body A by body B. So the first subscript is the body that you've chosen to isolate. The second one is the one applying the force. When you isolate a body and draw a free body diagram of it, one way to think about it is the body that you're isolating is the first subscript in every force vector, you know. So like if you do a free body diagram and all of everything is represented with this double subscript notation, every one of those forces should have the chosen body as the first subscript. So let me do an example similar to the last one I did, but this time I'll do it with this naming convention. So let's say we have two blocks stacked on top of each other. and say there's friction between these. And the top one is 20 kilograms, and the bottom one is 50 kilograms. And we have a 100 Newton force acting down, and a 50 Newton force acting to the side. And we'll assume that all contacts have friction. Then a free body diagram of the 20 kilogram. It has a weight force acting down of 20 times 9.81. That's 196.2. And a 50 Newton force there, a 100 Newton force there. And then continuing around the boundary, the only other place where there's contact with the outside world is here. And that's the force applied to the 20 by the 50. And then if I isolate the 50 kilogram, the weight is 50 times 9.81, so 490.5. The 100 and the 50, they're not applied to the boundary of the 50, so they don't show up. But if you go around the boundary looking for contact, when you get to the top, there's contact with the 20 kilogram box. So at the top, there's a force vector. This time we'd call it the force on the 50 by the 20. And at the bottom, you could call this the force on the 50 by the ground, something like that. Yep.
For the free body diagram of the 20, the vectors 50 and 100,
Mm-hmm.
is there a reason why we just leave them as numbers without units or labels?
No, not really. I don't know why I'm in that habit, but I think, okay, well, I suppose this is why I picked up that habit. Here, like in the diagram that shows the problem, there's all sorts of numbers, all sorts of things, so I'm trying to make it clear what are, I'm making a distinction between the forces and maybe the measurements and angles and other stuff. Here on the free body diagram, everything is forces, so yeah, right. I suppose that's why. But any other questions about that? Okay, and here is the really nice thing about that naming convention. Newton's third law. I'm going to abbreviate that N3L. That's the one that says every action has an equal and opposite reaction. How anybody made any mathematical sense out of that sentence, I have no idea. But for us, this is much easier to use mathematically. Newton's third law means this. The force on body A by body B is negative force on body B by body A. Like I said, when we have forces with known directions, we're not going to label them using this subscript notation because they're going to have scalar variables associated with them. So to use Newton's third law with forces with known directions, you just switch the force direction and keep the scalar variable or value the same. You know, keep the associated scalar the same. Okay, so let's do a couple of examples. First, let's say we have two blocks in contact with each other. There's a 50-kilogram block that's pushed up against the wall. And touching it is a 30-kilogram box. And then there's a 100 Newton force applied this way. Draw free body diagrams of each box. And we're going to assume that all the contacts are frictionless. So first, a free body diagram of the 30. We have the weight. 30 times 9.81 is 294.3. There's the 100 Newton force on the left. The ground applies a pushing contact, so it's perpendicular to the surface toward the chosen body. And I'll call that N30. And then when we get to the right side, there's a pushing contact from the 50 kilogram. So that's perpendicular to the surface toward the chosen body. I'll call that R. And then the free body diagram of the 50 kilogram box. There's the weight. That's 50 times 9.81, so 490.5. At the floor, there's a pushing contact. I'll call it N50. At the wall, there is a pushing contact, so it's perpendicular to the surface toward the chosen body. I don't know, I'll call that F. Keep going around, and you get to the left side. There's contact with the 30 kilogram box. Since all that is switching bodies, dealing with this contact force, we're going to use Newton's third law, and that says switch the direction of the sign, switch the direction of the arrow, and use the same scalar. Yeah.
So the force, the reason why you don't have to use a subscript is because you only have one force?
The reason I don't use the subscript is because these are forces with known directions, and so these are all scalars. You only use the subscript if your variables are vectors.
Okay, so like in the case where we have an incline, that would...
Yeah, in the case of a friction contact, those are unknown directions, so and that's the example I'm going to do right now, is one with friction contacts, and then we'll use that subscript notation.
That's what you're saying, not only vectors, not scalars.
That's right. Yeah. You don't want to use it here because it lures you into thinking, like if you called this F3050 and you called this F5030, that would lure you into thinking that this is the opposite of that. But we've already made it the opposite by changing the arrow directions. Yeah, and so it would give you a double negative, and it would mess your signs up. You get your signs backwards. So you only want to do it with vectors. Okay, so let's say that there's an incline and a 2 kilogram block and a 1 kilogram block and a force straight downward of 20 newtons. And both of these contacts have friction. And we want to draw a free body diagram of each box. So a free body diagram of the 1 kilogram. There's a weight force of 1 times 9.81. There's a downward force of 20 newtons. And then there's a friction contact that I'll label as the force on 1 by 2. And then the 2 kilogram box there's a weight of 2 times 9.81, so 19.62. Then there's a friction force applied to box 2 by the incline, F2I. And then when we get to the top, there's a force on 2 by 1. So that's F2.1. And Newton's third law says that that's equal to negative F1.2. And so what's the point? How does Newton's third law help us at all? It just changed the way we labeled this. In both cases, it's a force vector. What does it do for us? Well, remember that we're always going to Newton's laws to try to use those equations to solve for the variables. And so we need to have enough equations to solve for the variables. Before we made that switch, we have 1, 2, 3, 4, 5, 6 variables we need to solve for, since each of these vector variables has 2 components. After we make that switch, we only have 1, 2, 3, 4 variables to solve for. So if we don't make that switch, we don't have enough equations to do it. It's impossible. Once we make that switch, we can. Cuts down the number of variables that you have to solve for, and you don't have any control over how many equations are available. Okay. Well, let's do some real problems where we actually calculate some of these loads. Any other questions before I go on to the example problems? So let's say we have an incline of 30 degrees. And good God, this problem is so complicated. Who wrote this? I'm making it easier. Okay, so let's say that we have one 3 kilogram box. And then there's a pulley, and that 3 kilogram box is connected to a cable that goes over the pulley, and hanging from it is a 1 kilogram box. And let's say that this is friction. And we want to know what's the cable tension, and second, we want to know what's the force applied to the 3 kilogram box by the incline. And like we're going to do in every problem in this class, we're going to assume that everything here is in equilibrium. There's no acceleration. Okay, so let's do free body diagrams of both of these and write out Newton's second law for both of these and see what we have. Hopefully we have enough equations to solve for the variables. So free body diagram, let's do the 1 kilogram first. So we have a weight force, 1 kilogram times 9.81. And now go around the boundary looking for contact. The only place that there's contact is the cable, so I'll write that as T. And now that we have the free body diagram, I'll write out Newton's second law. Newton's second law says we add up all the forces, and those have to equal 0 as long as it's in equilibrium. So to write these as force vectors, we have 9.81 acting down, so 0, negative 9.81. T acting up, so 0, positive T. and that's equal to 0, 0. So that gives us two equations. The first one just says 0 equals 0, so that doesn't help. It's better than saying 0 equals 6, though. And then the second one says, t is equal to 9.81. So that's no good, but this gives us something useful. Well, I solved for t, so it says negative 9.81 plus t is equal to 0. Any other questions about that step? Okay, and then the free body diagram of the 3 kilogram box. We have the weight. That's 29.43. And now going around the boundary looking for contact. There's contact with the incline. What do we know about that contact? It's friction, so I'll call that the force on 3 by the incline. And then keep going around, and the only other place that there's contact is the tension force. Well, that's a single cable that's just going over pulleys. We're assuming it's massless, and the pulley is massless and frictionless. And so the tension here is equal to the tension at the other one. So this is equal to T, which is equal to 9.81. Because that's a single cable. And now we have to put that into Newton's second law. So Newton's second law says this force vector, F3I, I'll break it into x and y components, plus 29.43 down, so 0, negative 29.43, plus, bless you, now this is at a sort of a funny angle in our coordinate system, so we're going to have to represent that as a number times a unit vector. So think of a coordinate system like this. There's x, there's y. This angle is 30 degrees. Did I give that angle? Yes, good. Okay, so to figure out a unit vector representing that direction, we start at positive x. You can think of going counterclockwise 180, backtrack 30, so cosine and sine of 150. And so that's 9.81 times cosine of 150, sine of 150. And that's equal to zeros. So that gives two equations. The first one says F3IX. Can someone calculate that for me? 9.81 times cosine of 150. .496, say, and that's equal to 0. And then the second equation says F3IY minus 29.43 plus, I think this one's just 4.905 is equal to 0. And so this one tells you that F3IX is equal to 8.496. And this one tells you that F3IY is equal to, what's 29.43 minus 4.905? 24?
Yeah, negative 24.53.
53. And so the force that the incline applies to the box, the force on 3 by the incline, is equal to 8.496, 24.53. Yep.
So our Fi, that would be like the friction force, the static friction force combined with the normal force.
That's right. It's just combined and lumped into one thing.
Okay.
And if you took this vector and found the projection onto a unit normal vector, that would give you the normal force if you cared. And if you found a projection parallel to the surface, that would give you the friction force if you cared about that.
Okay.
So yeah, that is the normal force and the friction force. It just isn't broken up that way. It's broken up into our coordinate system axes.
Okay.
Question?
So all you got the 8.49 and 4.9.
How did we get those? That's from the unit vector representing that cable force. That's the cosine and sine of 150. Times 9.81, yeah, right. That's our first thing we calculated. That's great. Yep. Yes, if it's moving, the tension is still equal, but what would be different if it was moving is that, notice that here the tension was equal to the weight of that hanging mass. If it was accelerating, that would not be the case. Yes? If you do it that way, just calculating the counterclockwise angle from the positive x-axis, the plus minus sign comes out for you, and you don't even have to think about it. But if instead you want to think about that as a right triangle and do the trigonometry, then you have to do the signs for yourself. Different people have different preferences on that. So just do it a way that's comfortable to you. Any other questions right now? Okay. Let's do okay, let's start this hard one. It's a complicated one. So let's say we have an incline again. Let's say that this angle is 40 degrees. And let's say that there's a cart that's 3 kilograms, and resting on top of it with friction contact is a box that's 2 kilograms. So there's friction here. And then there's a pulley that connects the 3 kilogram cart to the ground. What are the cable tension and the force applied to the 3 kilogram by the incline? Oh, and the force applied to the 3 kilogram by the 2 kilogram. Okay, so before I start doing this, I don't know if we'll have time to finish this, but take a couple minutes and draw the free body diagrams for each of those 2 boxes. We run out of time. So free body diagram for the 2 kilogram. We have the weight, 19.62. And then the only other place there's contact is at the bottom, and that's a force vector, since that's a friction contact, on the 2 by the 3. And then a free body diagram of the 3 kilogram cart. There's a weight of 29.43. And then at the bottom, that's frictionless, so that's a pushing contact. So that's perpendicular to the surface toward the chosen body. I'll call that N. And then there's a cable tension, T. And then at the top, there's a force on 3 by 2, which is the negative force on 2 by 3. And now to solve this problem, I'll finish it on Tuesday, but to solve it, you just do Newton's second law for the second one. Write these as vectors, set them equal to 0. And for the third one, write these as vectors, add them up, and set them equal to 0. And it'll give you a system of equations so you can solve for all your variables. Yes? The F3 on 2 I wrote as negative F23. Oh, where is it in here? Oh, the incline. This here that I represented as a normal force with a known direction is the force on 3 by the incline. But it isn't going to appear that way in our equations. Any other questions? All right. Have a good Labor Day.